Academic Diadem Earth. Convert 273.15 milliliter at 166 kilopascal to its new volume at STP. You need to know that at STP volume is in liter and at STP pressure is in ATM and better still millimeter mercury. So at 760 millimeter mercury we have 1 ATM, and at 1 ATM we have 101.3 kilopascal. So if we know that when 103 divides 760 millimeter mercury, 101.3 divides this, you have 7.5. You have 7.5. So when 101.3 divides 760 millimeter mercury, you have 7.5. So anytime you're converting from kilopascal to millimeter mercury, simply multiply the value. Multiply the value by 7.5 to get millimeter mercury. So if you know that, you need to know that at STP, the second pressure will be 760 millimeter mercury because they said STP. So that will be your P2. Why P1? P1 is 166 kilopascal. Now the V2 is what we don't know. V2 is what we don't know. So if you know this now, which formula relates volume and pressure? Boyle's law. Boyle's law. 273.15 divided by 1000 will give us 0.27315 liter. And 166 kilopascal multiplied by 7.5 will give us 1245 millimeter mercury, and that is our P1. P2 is 760 millimeter mercury. Reason is because they said at STP. So P1 is 1245 millimeter mercury. V1 is 0.27315 liter, and this is equals to P2, which is 760 millimeter mercury times V2, which we don't know. That's what we're looking for. That's what we're looking for. Yes. So to get this, we simply multiply. And when you finish multiplying, you're supposed to have, when you punch that, you're supposed to have. So this will give us 331.877 equals to 760 V2. So to get V2, we have to divide both sides by 760. So when we do that, we're going to have 760 cancel 760. So we'll get V2. And when you punch that, you're going to have 0.437. And you know that this is an STP, and STP volume is liter. So that's that. Now the fourth question. The fourth question says, find the total pressure of a gas containing 750 torr of N2, 200 O2 torr, and 150 torr pressure of argon. Whenever you're talking about just pressure and they're telling you to find total pressure, it simply means that this is all about Dalton's law of partial pressure. And Dalton's law of partial pressure states that the total pressure of gas is equal to the sum total of the individual partial pressures of all the gases. The total pressure of a gas is the sum total of the partial pressures of the gas. So when I have a gas A, gas B, gas C, the total pressure will be the sum of A, B, C. So solving that, we're going to have So since the whole pressure is in torr, the unit of the pressure is in torr, so let's leave it in torr. So the total pressure is going to be the sum of partial pressure of nitrogen, partial pressure of oxygen, and partial pressure of argon. And when you do this, you're going to have 750 plus 200. That gives me 950 plus 150. And you put this, that gives me 1100. So if you do this, you're gonna have, and this is 750. If you put this 50 here, because 800, 900, 1000, 1100. So this is giving me 1100. And this is called the Dalton's law of partial pressure. This is Dalton's law of partial pressure. Note it. Number 5. It takes 3.12 seconds for a sample of krypton to effuse from one compartment into another at a certain temperature. Determine the time it takes for an equivalent sample of neon to do the same job. Whenever you hear effuse, whenever you hear diffusion, simply know that we are talking about Graham's law of diffusion. And what does this say? Graham's law of effusion states that Graham's law of effusion, not diffusion, of effusion states that the rates of diffusion of gases is inversely proportional to the square roots of the molar masses of the gas. Graham's law of effusion states that the rates of diffusion of gases is inversely proportional. The rates, when we talk about rate here, we mean velocity. Is inversely proportional to the square root of the molar masses. So look at this. This is R2, this is M1. And you know that if you increase the molar mass or the mass of something, it means that if the mass is increasing, if you have more load or more work to do, it requires more time. So as the load is increasing, as the molar mass is increasing, time is increasing. So it's the same thing as saying rates of the diffusion of gases is inversely proportional to the time. So molar mass and time, they are directly proportional. So when a question is asked and you're given molar mass and you're given time, you just make use of this. When a question is given and you're given rates of diffusion and you're given molar mass, you make use of this. And when this question is given and you're given the three, you can make use of the three formulas. So this is it. So naturally, we see more questions on this. But when cases of time come, you now make use of what you have. So it can be just these two, or just these two, or just this and this. So the summary of what his law is saying is that the lighter you are, the faster you can be. So if you are a lighter gas, you will travel faster than heavier gas. A heavy gas will tend to be slow. You can travel slow. You travel slow when compared to lighter gas. That's it. That's the summary of his law. And we know that diffusion is more or less something you can remember when you think of dilution, dilutes. When you hear something dilutes, you hear somebody say dilute something, it simply means that person needs it to move from higher concentration to low concentration. So that is the same way with diffusion. Diffusion is talking about the movement of gas or the movement of molecules from a region of higher concentration to a region of lower concentration. So using this, we'll solve that question. So we know that the molar mass of neon is 20.18, and that the molar mass of krypton is 83.8, and the time it takes neon is 3.12 seconds, and that of neon we do not know. So I need you to go through this. So when you do that, when you do 20.18 divided by 83.8, you're going to have 0.2408. Take the square root, you're going to have x all over 312. So the formula is supposed to be square root of molar masses equals to T1 over T2 without a square root. Pardon. So it's the same thing as the rates, but time is directly proportional. Y rate is inversely proportional. It's supposed to be this way. So when you do this very well, you're going to have this. And when you now do cross multiply, when you take the square root of 0.2408, you do the square root, you're going to have 0.4907. At this point, we can easily cross multiply. This is standing all over 1. You can do 1 times x, then 3.12 times 0.4907. Whatever we get is our x in seconds. So please, Graham's law of effusion states that the rates of diffusion of gases is inversely proportional to the square roots of the molar masses. And when you check it, this is directly proportional to the time. So as the load increase, the time required increase. So you need to know that. Now, whenever you're talking about gases, you need to know these 3 laws. One is ideal gas law. Ideal gas law. 2 is combined gas law. 1, 2, 3. 3 is Charles' law. 4 is Boyle's law. Number 5 is Gay-Lussac's law. Number 6 is Avogadro's law. Number 7 is Dalton's law. Number 8 is Graham's law of effusion. And what is effusion? Effusion is diffusion. Effusion is diffusion through a hole. So these 8 laws, and these 8 laws, from these 8 laws, these six are connected. You can get everything on this, everything here from ideal gas law simply by doing, let's do it. So for ideal gas law, this is it, ideal gas law. We simply need to know that ideal gas law is PV equals to nRT. Now combined gas law is simply making R subject of the formula. We have PV all over NT. And you know that initial must equal the final. So we have that this is going to be equals to P1 V1 equals to P2 V2. That is for combined gas law. Now in Charles law, then you know that all over N1 T1 all over N2 T2. Now for Charles law simply states Charles law simply states that at constant pressure, volume and temperature are directly proportional. So when we cancel this, we have Charles law. Because what is left is volume and temperature. That is Charles law. Now for Boyle's law, let me have the same combined gas law here. N1 T1 equals to P2 V2 all over N2 T2. Now Boyle's law is saying that at constant temperature, that volume and pressure are inversely proportional. So cancel this. This is Boyle's law. Now the next one is Gay-Lussac's law. Gay-Lussac's law is saying that at constant volume and pressure, let me use the same Boyle's law. Let me use the same combined gas law. P1 V1 all over N1 T1 equals to P2 V2 all over N2 T2. So using the same combined gas law, Gay-Lussac's law is saying that at constant volume and amount in mole, that at constant volume, that pressure and temperature are directly proportional. Take for example, if you're boiling water, if you heat it to an extent, at a point when it gets heated, you notice that the collision increase. The molecules of that water starts shaking. So as you increase temperature, you increase pressure. That's what he's talking about. And the same thing, Charles law is saying that as you apply air to balloon or to your football, that as you apply air, volume increase. And in volume, when temperature exceed limits, you can break the volume, you can break the container. So increase in volume equals increase in temperature. But Boyle's law is saying that as you increase space, for example, if you pour 1 cup of water inside an empty 20-liter jerry can, it will look as though there is no water. But if you pour that same water inside a container that is very small, you will notice it very well. So as you increase the container, you reduce the collision. Take pressure to be collision, force over area. Now let's move to the next one, which is Avogadro's law. Now we know that anything about Avogadro is always more of mole. It's the one that gives number of constants, if you remember. So using the same combined gas law, if you remember, we have Avogadro's law, Avogadro's constants, number of particles, which is the same thing as 6.022 times 10 raised to the power 23. So that's Avogadro's constants. So if you remember that, you relate anything Avogadro with mole. So if that is the case, if we have this, Avogadro said that at constant temperature and constant pressure, the volume and amounts in mole are directly proportional. So at constant pressure, constant temperature, that is ignoring pressure, ignoring temperature, that volume and amounts in mole, amount of substance, are directly proportional. So V1 over N1 is equals to V2 over N2. So I hope you enjoyed this. Academic Dad.